Today, on how it's made. Windshields. We'll show you the inside view about how they make them. English saddles. We have the unbridled facts. Butter. We visit a factory that puts out quite a spread. And post clocks, when time is of the essence. Drivers of the earliest cars had only goggles to shield them. So to protect people from the elements, the glass windshield was invented in 1904. But there was a danger. They would shatter on impact, injuring people. Glass lamination solved the problem. It was shatterproof, a real scientific breakthrough. To make a windshield, they start with a plain sheet of glass. An automated plotter moves a cutting wheel over it and the wheel scores the glass. Now, a robotic arm brandishes a torch. It moves along the score line and the thermal shock completes the cut. This is the best way to cleanly cut through glass. Next, a robot suctions up the cut piece of glass and transfers it to the next station, where it pushes the glass against a series of sanding belts. This takes off the sharp edges. It's called seaming. Now a conveyor belt takes the glass through some soapy water to clean it up. Then nozzles spray the glass with a mix of talcum powder and water. This will prevent the glass from sticking to a second sheet of glass. A robot now sets that second piece of glass on top of the freshly sprayed one. This is a temporary arrangement. The two sheets of glass are layered for processing, but will be pulled apart later. Next, they silkscreen black paint around the border of the glass that will eventually be the inner part of the windshield. Then automated arms carry the glass to a station where samples are inspected visually. After that, rollers transfer the glass to automatic squaring pucks, which position them. And then a robot lifts the sheets of glass and carries them to 4 metal pins. The pins recede, and the glass falls onto a bending iron. The iron is shaped like a specific windshield. The conveyor takes the bending iron with the 2 glass sheets into an oven called a bending leer. The leer heats the glass sheets to 750 degrees Celsius, causing the glass to sink into the shape of the bending iron. Then the glass goes through a slow cooling cycle to anneal or toughen the new shape. Next, a robot picks up a sheet of vinyl cut in the shape of a windshield. It takes the vinyl sheet to one of the newly shaped pieces of glass, just separated from the other piece. Then another robot lowers the other identical piece of glass onto the vinyl. And that's the formula for glass lamination. 2 layers of glass with a piece of vinyl between them. In the event of an accident, the windshield will fracture but not totally shatter because the vinyl will hold most of the broken glass together. But at this point, there's no clear view through that milky white vinyl. That's why the windshield is headed to a machine called a nipper. The nipper presses the windshield between a series of rubber rollers, squeezing out air pockets in it. As the air is removed, the view through the vinyl gets a bit clearer. Now, squaring pucks position the windshield, and a robot sticks brackets for the rearview mirror onto it. This big blue chamber is an autoclave. It's like a pressure cooker. After about an hour in there, any remaining air pockets in the windshield are removed. A rail system transports the tub full of windshields to the inspection station. Here, each windshield undergoes a close-up inspection by a human. He searches for scratches, chips, or any contamination between the glass and vinyl layers. Now, they place a 2¼ kilogram steel ball into a pulley system that raises it 4 meters high. Yes, this is a crash test for a sample windshield. The ball represents a driver's head. The ball hits the glass but doesn't go through. which means the windshield has passed this safety test. Now they view the windshield through polarized light, which reveals stress defects, but only a trained eye can spot them. Once it's decided that everything looks good, the windshield is ready for the road. And the view from the driver's seat is now as clear as glass. Saddle making goes back thousands of years, but in modern times, saddle makers have realized that a bad-fitting saddle can be a real pain for the horse. The rider will feel that pain in the animal's attitude and performance. So now, saddles are often custom-made to fit both the horse and the rider. It's a little 21st century horse sense. To make an English saddle, they attach both rigid and flexible steel strips to a frame made of polyurethane, which is called a tree. Then, they rivet a stirrup bar through the tree to the steel that's just been fastened to the underside. With a jigsaw, a worker cuts a hole in the tree and then glues foam for cushioning. Now he coats the back of the cantle, or seat, with glue and sticks a piece of leather onto it. He crimps the leather around the edges of the tree. And using a special tool for cutting leather, called a clicker knife, he carves away the extra material. Then he sprays glue onto the top of the tree and presses a layer of foam onto it. Using an ordinary kitchen knife, he slices away excess foam at the sides and carves out more foam to shape the seat. Then he shaves the edges with a rasp. Next, he layers 2 more foam pieces over it and sculpts and shaves those layers. He runs a measuring stick along the seat to make sure it's even, and then pastes a piece of black foam on top to add even more cushioning. Now, with a half-moon blade, another worker slices a piece of leather to make a saddle flap. She follows a trace out of the rider's leg. She feeds the flap piece into a skiving machine. Its circular blade shaves the edges of the leather as a wheel pulls it through. The thinned-out edges will be easier to sew later on. Next, she heat stamps the saddle logo onto the flap. She also stamps the model, serial number, tree and seat size onto the saddle. Now she glues foam to a hard piece of leather to make a knee pad and sticks softer leather on the top where the rider's knee will rest. Then, using a piece of whalebone, she draws the leather tight around the edges so that it's smooth on top. Whalebone is used because it doesn't scar or scratch leather. Next, she seals the front edges and then crimps them together, the way a baker crimps the edges of a pie. She pulls the leather tight from the backside and paints glue onto the fatter rim. Then she brushes glue onto the flap and presses the knee pad and flap together so the glue sticks. She hammers them to strengthen the bond. Then stitches them together along that glue line using a big industrial sewing machine. With a steel prod, she stuffs a wool and synthetic mixture into the panel which will be on the horse's back. It's being stuffed with a certain horse in mind. The amount of stuffing used depends on the shape of the horse the saddle is being made for. She hammers it flat with a rubber mallet and then stitches the panel to the top of the saddle. To sew through the leather layers, she makes a hole with an awl and then pulls the needle and thread through it, spraying water to keep the leather soft. She hammers the seam to get rid of any gaps between the layers. But sewing the back of the panel to the bottom of the seat is a bit trickier. She uses a curved awl and needle to work with the contours. It's taken about 25 hours to piece together this customized English saddle, and that's with no horsing around. This is the Saddle Tech device. and they use it to make sure the saddle measures up. It measures it in 4 sections. Now it's onto the tree machine. It adjusts the gullet plate, the piece of rigid steel that sits above the horse's withers. Plastic panels support the saddle, while a hydraulic press bends the plate to fit the measurement. Now it's time to saddle up and check out the horsepower from this custom-made seat. Butter has a rich history. The ancient Romans used it as a beauty cream and to treat burns. Even the Old Testament mentions butter. Abraham served it to angels. Back then, people made butter by shaking milk in bags of animal skin or in hollow logs. Today, its glorious taste is a product of modern technology. Butter making begins with a tanker truck delivery to the dairy, 30,000 liters of raw cow's milk. Workers test it for consistent color and odor before unloading it through vacuum-pumped hoses. They pump the raw milk into a machine called a separator. The separator spins, dividing the raw milk's fat from the rest of the liquid. The fat is called buttercream, and the rest is skim milk. The essential ingredient in butter is the buttercream. It's thick, off-white, and approximately 38% fat. Some of it goes to make 2% milk. A worker adjusts a valve to reinsert some into the skim milk. The resulting 2% milk is more watery than buttercream and is white. The less the fat content, the thinner and runnier the milk is. Back to the butter making. They put the buttercream in what's called a bulk tank, where mixers stir it to maintain the consistency. After pasteurizing and then aging the buttercream for 24 hours, workers prepare to transfer it into another machine called the churner. First, they clean the inside by filling it with water mixed with iodine. This removes any germs left behind by the previous batch. They spin the churner for about 5 minutes before rinsing it out. Next, they pour in 1,500 liters of buttercream, filling the churner about halfway. It's important to leave some room so that the air released in the churning process can escape through 2 vents in the churner. The churner spins at 28 rotations per minute, about the speed of a clothes dryer. This causes the buttercream's fat molecules to bunch together, releasing water and air. Every 5 minutes, a worker stops the churner and regulates the air vent on top. When he feels there's no more air escaping, he closes the valve and restarts the machine. After 30 minutes of churning, the fat molecules in the buttercream are creamy clumps known as popcorn butter. These clumps stay trapped in the churner, while the remaining liquid, called buttermilk, flows out a drain at the bottom. A vacuum pump system sends it through hoses to a nearby container. This draining process takes about 10 minutes and produces about 800 liters of buttermilk. This dairy uses the buttermilk to make ice cream. The popcorn butter, all 684 kilograms of it, has the same consistency as regular butter at room temperature. A worker now flavors it with 14 kilograms of salt. This dairy also makes unsalted butter. The worker closes the churner by sealing the glass window with a rubber ring and a metal collar. This keeps the internal air pressure roughly equal to what's outside the churner. Doing this ensures the churner works efficiently. Another 30 minutes of churning and the fat molecules thicken even more and blend with the salt. What results is butter, which is yellow because of its natural vitamin A. Next, a worker scoops about 30 kilograms of butter into a milling machine. The mill moves the butter into the final production phase, where it'll be shaped and put into packages. This machine squeezes butter into an injector that's shaped like a block. The injector then deposits blocks of butter into open packages. The packaging paper has an aluminum outer coating. This prevents light from penetrating. Light can make the butter rancid. Each sheet is 26.5 centimeters long and 19 centimeters wide. Before the butter is inserted, a plastic former bends the paper into shape. This mill operates 4 days a week, churning out up to 33 blocks per minute. That's a fairly small quantity compared to some dairies. But this relatively slow pace allows greater quality control. To monitor the mill's precision, workers check every 15th block to ensure it weighs exactly 455 grams. The dairy then ships the butter to stores in refrigerated trucks. Clocks on posts became popular fixtures in town squares during the 1800s. Railways were spreading fast, and these public clocks helped people get to their trains on time. Today, post clocks are often designed to look like they're from the past, but the technology that goes into making them is actually very up to date. It all starts with what's called a transfer sheet. A worker positions it over an aluminum disc that'll become the clock's dial. She removes the sheet, sprays on a chemical, and repositions it. The chemical will act as a release agent, detaching the vinyl numbers from the sheet so that they transfer and stick to the dial. She then peels the sheet off. This worker prepares a more elaborate model with numerals in 23-karat gold leaf. After coating them in glue, she applies a hair-thin sheet of gold. Then she gently brushes the gold onto the numeral. Using a computer-guided cutter, workers cut a half-centimeter thick sheet of aluminum into a clock hand that's nearly a meter long. To boost the hand's rigidity, they crease it in a press. This structurally reinforces the metal, helping retain the hand's shape over time. A 42.5-gram counterweight will balance the hand when it rotates. Here, a welder builds the post by fusing a base and column made of cast aluminum. On another model, workers attach the housing for the clock head. This clock will have 4 dials. Other models have 2. In the paint shop, workers give the base, column, and head 4 coats of paint. After applying some lubricant on a steel shaft, called a stud, a worker installs one of the clock's 8 brass gears. Brass because it's strong and durable. A steel loop called a snap ring holds each gear in place. One gear has what's called a vane to regulate the pulsing of the gears. Next, a worker attaches the shaft and gear that'll control the minute hand. Altogether, the gears form what's called the clock movement. He screws on a brass panel called a backplate to hold the clock movement in place. Then he attaches an electronic circuit board that'll later connect the clock movement to another component. He installs a 115-volt motor to supply the clock's electric power. Finally, he connects power wires and turns on the clock movement. Here, he's checking to see that everything's properly linked and that the gears are moving well. This company makes clock movements for clocks ranging in diameter from just 22 centimeters to more than 9 meters. The gears in the largest clock are nearly a meter wide. Here you can see how the shaft that'll hold the minute hand revolves inside what's called the sleeve of the hour hand. A worker attaches the clock movement to the back of a dial. Then he ties wires through what are called glass standoffs. These standoffs will cradle the clock's neon light. The neon tube encircles the clock's perimeter. It attaches through holes to a transformer hidden behind the dial. He fastens the tube with rust-resistant copper wires. Next come the hour and minute hands, now painted black. He uses an Allen wrench to attach them to what's called the hand hub. This hub holds the hands on the shaft that's part of the clock movement. The assembled dial now goes into its casing. The casing has 2 parts: an aluminum ring, called a bezel, around a glass cover known as a crystal. He connects a wire to link the dials so that they'll move in sync. The worker then inserts this casing into what will be a 2-dial post clock. Workers then turn on the neon clock light to test it. Once the post clock's installed, a built-in sensor turns the light on at dusk and off at dawn. Inside every clock is a controller that sets the time. It's linked to a satellite through a global positioning system. The GPS tells the satellite where the clock's located to set the correct local time. After starting up, the controller takes 6 minutes to adjust the hands to the exact time, which is determined by an international observatory in Greenwich, England. This company's post clocks can stand more than 6 meters high and cost up to $35,000, lending a whole new meaning to the phrase, time is money. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.